In this video, we are going to be looking at Equilibria, which is all about reversible reactions. In multi-choice questions, they most commonly ask about the definition of equilibrium. The wording can be quite confusing, so as soon as you see something like this, when they're clearly asking about a definition about equilibrium or dynamic equilibrium, take a minute and jot down yourself what you know about equilibrium to begin with. At equilibrium, the rates are equal, concentrations are constant, CC, concentrations constant. So let's look at what they've given us here and see if anything pops out. Chemical reactions are in a state of dynamic equilibrium only when A. The reaction involves no enthalpy change. Well, that's just nonsense. You occasionally get reactions that have a very small enthalpy change, but no enthalpy change is not a probability. B. The concentrations of reactants and products are equal. Again, no. Concentrations constant. CC, concentrations constant. The activation energies of the forward and reverse reactions or forward and backward reactions are equal. No. It's possible, but it's highly unusual, but it's really not relevant to equilibrium. We'll just score that one as well. D. The rate of the forward reaction equals that of the backward reaction. Yes, that fits what we already know. Rates are equal, concentrations constant. In this question, they're asking a similar thing, but they're being sneaky about their wording. What you have to remember is that rates are equal, concentrations constant. In a reversible reaction, equilibrium is reached when A. Molecules of reactants cease to change into molecules of products. That is not true. The rates are equal. It's a dynamic equilibrium. The reactions are still going on, so that's wrong. B. The concentrations of reactants and products are equal. No, they're not. Concentrations constant. CC. B. C. The concentrations of reactants and products are constant. Yes, and we'll just check our final one to be sure. D. The activation energy of the forward reaction is equal to that of the reverse reaction is not relevant in equilibrium. As long as you remember rates are equal, concentrations constant, CC, you should be fine with the definition questions. So here's a past paper question looking at concentration. The addition of which of the following substances would move the equilibrium to the right? Now, in a question like this, first of all, go through your equation, identify what's there, and then try and match it up. Is there anything that directly matches here that's going to mean we're increasing the concentration of a reactant or a product? If we're increasing a reactant, we'll shift to the right. If we increase a product, we're going to shift to the left. So we'll look for the direct things first. The first one is hydrogen. So there's hydrogen here. There's hydrogen ions here, but that's not the same as hydrogen. Hydrogen chloride, effectively hydrochloric acid. So if we have hydrochloric acid, that's more hydrogen ions. That would shift our equilibrium to the left. That's not what we're after the shift to the right. Sodium chloride would be adding more chloride ions. Again, that would shift our equilibrium to the left. Sodium hydroxide. Now, in your first look, you're like, oh, there's no hydroxide ions. But remember, hydrogen and the hydroxide can react together to give us water. When that happens, we're reducing the concentration of one of our products. The rate of reaction for the forward reaction will increase. The equilibrium is going to shift to the right. So here's a past paper question on pressure. In which of the following would an increase in pressure result in the equilibrium position being moved to the left? Before we get into the equations, go round and highlight anything that has gas in it. And I think most of these are gas. This bottom equation is the only one where not everything is gas. We're now going to compare the moles of gas in the reactant side and the product side for each equation. So for A, there's 4 moles of gas on the reactant side and 2 moles of gas on the product side. What I'm looking at here are the coefficients in the balanced equation. So 1 nitrogen, 3 hydrogens giving me the 4, and the 2 in front of the ammonia gives me 2 there. So I'll do that for every equation here. It's a good place for you to pause the video and count up the moles of gas yourself and check that we get the same answer. So pause now and just press play again when you're ready to check. So looking at the answers, we have 2 where we've got the same number of moles in the product side as the reactant side. That means a change in pressure won't affect the position of equilibrium at all in these reactions. The question says an increase in pressure will result in the equilibrium being moved to the left. So that's over to the reactant side. So that tells me that there should be fewer moles on the reactant side than there is in the product side. So increase in pressure will shift the equilibrium to the lowest moles of gas. We want it to shift to the left, so left must have lowest moles of gas. Now we just have to examine our answers here, and we find that C has the lowest moles of gas. So an increase in pressure will shift the equilibrium of this reaction over to the left. Ethanol is manufactured by reacting ethane with steam. And we've got our reaction there, and when we see the enthalpy change shown at the right hand side, that's shown as the enthalpy change for the forward reaction. And here we can see it's a negative value, so that tells us it's exothermic. So the forward reaction is given out heat. The reverse reaction is taken in heat. So the forward reaction hot, reverse reaction cold. Which set of conditions would give the best yield of ethanol at equilibrium? And if we're looking at the answers there, it's asking about temperature and it's got information about pressure as well. So we're going to have to decide what's the best temperature and the best pressure to get the best yield of ethanol. We're not talking about how quickly we're making it here, we want the maximum yield of ethanol. So we'll focus first on the temperature, and as we said, forward reaction exothermic, reverse reaction endothermic. If we heat up our reaction, it will shift away from the hot side over to the reactant side, over to the left, and we'll get more of the reactants. We don't want that. We want to shift it over to the right, to the product side, to make it more of our ethanol. So if we cool it down, decreasing the temperature, our equilibrium will shift to the hot side, shift to the right, and we'll make more of our ethanol. We'll get an increased yield of ethanol. So we need to look for ones where there's a low temperature. So we get 2 possibilities there that have a low temperature. Now let's look at the pressure. The effective pressure is all about moles of gas, so let's look at the moles of gas we have. So at the reactant side, we've got 2 moles of gas at the reactant side, and at the product side, we've got 1 mole of gas. That tells me I've got low pressure at the product side and high pressure at the reactant side. If I want to shift my equilibrium towards the product side to get a greater yield of ethanol, I have to do the opposite of what the pressure is at that side. So it's low at that side. That means I need a high pressure to shift it to the right. And then I look at which of my options has the high pressure, and it's option C. C is our answer. Which line in the table applies correctly to the use of a catalyst in a chemical reaction? And it's asking us about the position of equilibrium. Catalyst does not affect the position of equilibrium. Effect on the enthalpy change for the reaction. If you've covered rates of reaction already, you'll know or be familiar with these diagrams, reaction pathway diagrams, and the enthalpy change for a reaction is the difference between the energy levels of the reactants and the product, this value here. If we add a catalyst to that reaction, it would lower the activation energy, So here is our activation energy for the uncatalyzed reaction. Here would be the activation energy for the catalyzed reaction. This is for forward because my arrows are starting at this level. But that's having absolutely no effect on the overall enthalpy change for the reaction. It's simply lowering the activation energy. So if we go back to our possibilities here, affecting the enthalpy change for the reaction, the catalyst has no effect at all on the enthalpy change for the reaction. It lowers the activation energy, but does not alter the overall enthalpy change for a reaction. So far we've looked at multi-choice questions. In the next couple of examples here, we're looking at ones from the extended answers section of paper 2. In bleach cleaner, an equilibrium exists. And we've got our equilibrium equation there. The label warns that the bleach cleaner should not be used with other products as it may release chlorine gas. Explain clearly why mixing the bleach with an acid would shift the equilibrium to the right, resulting in the release of chlorine gas from the bleach cleaner. So 2 marks for this, 2 points thereafter. The main thing they want you to realise is that acid has hydrogen ions in it. So your first mark is for saying that adding acid increases the hydrogen ion concentration. By adding the acid, we are increasing the concentration of hydrogen ions, increasing the concentration of one of our reactants. So that is going to be shifting the equilibrium to the right, and it will produce the chlorine gas. So the second mark is for saying the rate of the forward reaction is increased. We're not needing to say what way the equilibrium shifts. They've already said in the question the equilibrium is going to shift to the right. So you're just explaining why it's shifting to the right. Adding acid increases the hydrogen ions, 1 mark. The rate of the forward reaction is increased, 2nd mark. So here we have an open question on equilibrium. How do we know it's about equilibrium? We've got our double-headed arrow there. Remember, there's no specific right answer or correct answer to these questions. You're trying to show an understanding, but really we're trying to bring everything together here that we've been thinking about. Cisplatin is a widely used anti-cancer drug. It can be produced in the following exothermic reaction. So we have the equation, and they've also given us in the table the cost of some of the chemicals per gram. Using your knowledge of chemistry, comment on how this process could be carried out to make the production of cisplatin as profitable as possible. First of all, going back to the equation, we've seen the reversible arrow is equilibrium, so if we want to make cisplatin, we're going to have to shift the equilibrium over to the right. So now we have to look at ways to do that. So really we need to be thinking about concentration, pressure, temperature and catalyst. So to shift this equilibrium to the right using concentration, we have to increase the concentration of our reactants. We also need to think about the profitability of this. We don't need to increase the concentration of all our reactants, just one of them even will increase the rate of the forward reaction, shift the equilibrium to the right and increase the yield of our product. Looking down at the table here, we can see that the cheapest reactant is the ammonia. It doesn't cost that much. So by adding more of the ammonia, we're going to have the desired effect. Also thinking about concentration and thinking about our concentration of products, think back to the Haber process where we could remove our products. One of our products is a solid, that's going to precipitate out. That'd be fairly easy, straightforward for us to remove from the reaction vessel. And then again, that's going to shift our equilibrium to the right and increase our yield of the product that we actually want. Next, looking at pressure. Pressure is all about moles of gas, and there's gas on our reactant side, but there's no gas on the product side. So 1 mole of gas on the reactant side, 0 moles of gas on the product side. So if I want to shift that equilibrium over to the right like we want, I'm going to have a high pressure. The high pressure is going to force the equilibrium over to the right, to the low pressure side, to get more of our product. We have to remember though that high pressure requires specialised equipment. So the likelihood is we'll have it at a medium pressure to force the equilibrium over to the right, but without it being too pricey for us, just keeping it profitable. Next is temperature, and there's no enthalpy value beside the reaction, but if you read the question carefully, it's telling us that it's an exothermic reaction. So exothermic, that's the hot side, and if we want to shift over to the hot side, then we've got to make things cold. So making it cold will shift the equilibrium to the right, increase our yield of the cisplatin. However, if it's too cold, it's going to slow the rate of reaction down too much. And so although we might get a high yield, it's going to take far too long for us to make it, for it to be profitable. So there has to be a happy medium. Finally, a catalyst could be used, and that just makes the whole process more economical. Remember, a catalyst does not affect the position of equilibrium in any way. It just speeds up both the forward and the reverse reactions. Now, it wouldn't be enough for you just to put these kind of bullet point bits down that I've put here. You're going to need to give the explanation. Doing this will shift the equilibrium to the right. Medium pressure, well, actually a high pressure would give us a higher yield. However, it's too expensive, so we'll use a medium pressure, and explain why that high pressure would have been the best for the yield, because there's fewer moles of gas on the product side. So you have to give your explanation concentration. Increase the concentration of the reactants will increase the rate of the forward reaction, shift the equilibrium to the right, greater yield of our product. Make sure you're using the cheaper reactant though, because we want this profitable. Temperature, we want it to shift to the right, to the exothermic side, so we need to get it a bit cooler. Not too cold though, or the rate will slow down. Finally, the catalyst mentioned that it speeds up the rate of reaction, but doesn't affect the position of equilibrium. So this question is a chance for you to bring together everything you've learned about equilibrium and really show your knowledge.